Welcome! In this video, we will tackle LeetCode problem number 846, titled Hand of Straights. This problem challenges us to determine whether a sequence of cards can be divided into groups of a specific size, following certain rules. We'll explore the problem, break it down, and solve it step by step. Let's dive in. In this problem, we are tasked with determining if we can rearrange a given set of cards into one or more groups, where each group contains exactly a specified number of cards, called the group size. The key condition is that the cards within each group must form a consecutive sequence. For example, if the group size is 3, then a valid group could be 1, 2, 3, or 4, 5, 6, but not something like 1, 2, 4, because 4 is not consecutive with 2. The input consists of two key pieces of information: the array hand, which represents the card values, and the integer group size. The output is a boolean that indicates whether it's possible to rearrange the cards to satisfy these conditions. Now, let's explore some examples to solidify our understanding of the problem. In the first example, we have the input hand equal to 1, 2, 3, 6, 2, 3, 4, 7, 8, and group size equal to 3. Here, the output is true, meaning it is possible to rearrange the cards into groups of 3 consecutive numbers. The valid arrangement is as follows: 1, 2, 3, 2, 3, 4, and 6, 7, 8. Each of these groups contains exactly 3 cards and forms a consecutive sequence. This example demonstrates that cards can be used in multiple groups, as long as the conditions of group size and consecutiveness are satisfied. Let's look at another example to see when the output would be false. In the second example, the input hand is 1, 2, 3, 4, 5, and the group size is 4. The output in this case is false, meaning it's not possible to rearrange the cards into groups of 4 consecutive numbers. While we can form one group, such as 1, 2, 3, 4, the card with the value 5 would be left over, which violates the requirement that all cards must be used. In contrast, in the third example, the input hand is 8, 10, 12, and the group size is 1. Here, the output is true because each card can form its own group, and there are no leftover cards. This shows that when the group size is 1, the condition is always satisfied as each card is treated as a standalone group. Now, let's consider some edge cases. First, if the group size is 1, the output is always true because each card can independently form its own group, regardless of the values in the hand. However, if the group size is greater than the total number of cards in hand, the output is always false because it's impossible to form even a single group of the required size. Additionally, if there are duplicate cards in the hand, the algorithm must ensure that these duplicates are allocated to separate groups correctly. Another critical scenario is when the values in hand have large gaps between them, which may prevent the formation of consecutive sequences and lead to an output of false. Finally, in cases where the hand contains values that repeat multiple times, such as 1, 1, 1, 2, 2, 2, 3, 3, 3, the algorithm must carefully distribute these duplicates while respecting both the group size and consecutiveness requirements. These considerations help ensure the solution handles a wide range of inputs effectively. To solve the problem hand of straights, we need to determine if the cards in the array can be grouped into sets of a specified size, where each group contains consecutive integers. Let's explore some approaches. The brute force approach begins by sorting the array and then searching for consecutive groups of the required size. After forming a group, the used cards are removed, and the process repeats until all cards are processed. However, this method is inefficient due to its repeated scans and nested loops, resulting in a time complexity of n squared, in the worst case. A better approach involves using a counting strategy. Here, we use a hash map to count the frequency of each card and sort the keys of the hash map. For each card, if it's still available, we attempt to form a group by decrementing the counts of consecutive cards. This avoids redundant computations and operates with an overall complexity of n log n, making it much more efficient compared to brute force. Additionally, there's another method involving a min heap. In this approach, all cards are pushed into a heap, and the smallest card is extracted to form groups of consecutive cards. The heap ensures that we always process the smallest available card first. While this method shares a time complexity of n log n, with the counting approach, it introduces more overhead due to repeated heap operations, such as insertions and extractions. After evaluating these strategies, the optimized approach using counting emerges as the preferred solution. It directly utilizes a hash map to track card frequencies and processes cards in ascending order. Sorting the keys ensures that groups are always formed correctly, avoiding invalid sequences or gaps. The clarity and efficiency of this method make it straightforward to implement while minimizing computational redundancy. The optimized counting approach is favored for several reasons. It is significantly faster than the brute force method because it avoids redundant work, and it is simpler to implement and debug compared to the heap-based approach. Furthermore, it scales well with large inputs due to its O, n log n, complexity. While sorting introduces some overhead, this trade-off is acceptable given the overall reduction in processing time. Compared to the heap-based method, the counting approach is more memory efficient and less complex to implement. In summary, this strategy strikes the right balance between simplicity, efficiency, and scalability, making it the ideal choice for solving the hand of straights problem. The Python implementation provided demonstrates this approach clearly, leveraging a counter to track frequencies and iterating through sorted keys to form valid groups. The problem hand of straights challenges us to determine whether the integers in an array can be grouped into sets of a specific size, where each set contains consecutive numbers. If we can achieve this grouping, we return true, otherwise, we return false. To solve this problem efficiently, we use a greedy algorithm in combination with a hash map. The greedy approach ensures that we always process the smallest card values first, which helps in forming consecutive groups, while the hash map helps us track the frequency of each card efficiently. The solution begins with input validation. Here, we check if the total number of cards in the array is divisible by the group size. If it isn't, it's impossible to divide them into equal groups, and we can return false immediately. Next, we count the frequency of each card using a hash map. For example, given the input hand 1, 2, 3, 6, 2, 3, 4, 7, 8, the resulting frequency map would look like 1, 1, 2, 2, 3, 2, 6, 1, 4, 1, 7, 1, 8, 1. This frequency map allows us to track how many times each card appears, which is essential for determining if we can form valid groups. After counting the frequencies, the next step is to sort the unique card values in ascending order. Sorting ensures that we always start forming groups from the smallest available card, which is critical for maintaining consecutive order. For instance, with the example hand, the sorted card values would be 1, 2, 3, 4, 6, 7, 8. Once sorted, we begin forming groups. For each card in the sorted list, if its frequency is greater than 0, we try to form a group that starts with this card. To form a group of the required size, we check if the next group size 1 consecutive cards are available, meaning they also have non-zero frequencies in the hash map. If we find that any of these consecutive cards are missing, we return false because it's impossible to form a valid group. When we successfully form a group, we decrement the frequencies of all the cards used in that group. For example, if group size equals 3 and we form the group 1, 2, 3, the updated frequency map would become 1 o'clock, 2, 1, 3, 1, 6, 1, 4, 1, 7, 1, 8, 1. This process is repeated until all cards are used or until we determine that no more valid groups can be formed. The final step is a simple check. If we successfully form groups for all the cards, we return true. However, if at any point a group cannot be formed, we return false. Let's review some of the key insights from this approach. The greedy strategy of always starting with the smallest card ensures that we minimize the risk of leaving any cards ungroupable. The hash map is a critical component because it provides O1 access to card frequencies, making our solution very efficient. Sorting the unique card values is another essential step, as it ensures that we process cards in the correct order to form consecutive groups. In terms of data structures, the hash map is used to store the frequency of each card, while an array is used to hold the sorted unique card values. Together, these structures enable an efficient and systematic way to solve the problem. For complexity analysis, the time complexity includes counting frequencies in O, n, sorting the unique card values in O, k log k, and forming groups in O, n. This gives an overall time complexity of O, n plus k log k, where n is the total number of cards and k is the number of unique cards. The space complexity is O, k, due to the hash map used for storing frequencies. Now, let's consider some edge cases that the algorithm needs to handle. First, if the group size is larger than the total number of cards in the hand, we can immediately return false since it's impossible to form any group. Next, we need to ensure that the algorithm correctly handles duplicate cards. For example, if multiple cards have the same value, the frequency count must be accurate to avoid forming invalid groups. Another important case involves non-consecutive cards or large gaps between card values. The algorithm should correctly identify when such scenarios make grouping impossible. Lastly, if all the cards in the hand are identical, the algorithm should return false unless the group size is exactly 1 because consecutive groups cannot be formed. Let's walk through an example to see the algorithm in action. Suppose the input hand is 1, 2, 3, 6, 2, 3, 4, 7, 8, with a group size of 3. The goal is to determine whether these cards can be grouped into consecutive sets of size 3. The process begins by counting the frequencies of the cards, resulting in the map 1, 1, 2, 2, 3, 2, 6, 1, 4, 1, 7, 1, 8, 1. Next, we sort the unique card values, giving us 1, 2, 3, 4, 6, 7, 8. From here, we start forming groups. We begin with the smallest card, 1, and form the group 1, 2, 3. After using these cards, the updated frequency map becomes 1 o'clock, 2, 1, 3, 1, 6, 1, 4, 1, 7, 1, 8, 1. Next, we move to the smallest card with a non-zero frequency, which is 4, and attempt to form another group. This time, we form 4, 6, 7. Updating the frequency map again gives 1 o'clock, 2, 1, 3, 1, 6 o'clock, 4 o'clock, 7 o'clock, 8, 1. Finally, we try to form a group starting with the smallest remaining card, 8. However, there are no consecutive cards available to complete a group of size 3, so no more groups can be formed. At this point, we observe that not all cards have been grouped successfully. Specifically, the card with value 8 remains ungrouped. Hence, the algorithm concludes that it is not possible to divide the given hand into groups of the specified size. The final output for this example is false. This illustrates how the algorithm efficiently identifies and handles cases where grouping is not feasible, ensuring correctness and optimal performance. This solution to the hand of straights problem uses a greedy algorithm with a hash map to ensure efficiency. First, we check if the total number of cards is divisible by the group size. If not, it's immediately impossible to form groups, and we return false. Next, we leverage Python's collections counter to count the frequency of each card in the hand. This gives us a dictionary-like structure where keys are card values and values are their counts. Sorting the keys ensures we always process cards in ascending order, which is critical for forming consecutive groups. For each card, if its count is greater than 0, we attempt to form a group of group size starting with this card. For each card in the group, we check if there are enough cards available to form the group. If any card in the sequence lacks the required count, the function returns false. Otherwise, we decrement the count for each card in the group. Finally, if all cards are successfully grouped, the function returns true. This approach processes each card at most once, ensuring an efficient runtime complexity approximately n log n, where n is the number of cards, due to sorting. Here, we begin by defining the method isNStraightHand, which takes an array of integers hand representing the cards and an integer group size indicating how many consecutive cards must form a group. The first thing we check is whether the total number of cards in the hand is divisible by the group size. If it's not, we immediately return false since it's impossible to evenly distribute the cards into groups of the specified size. Next, we use a tree map to count the frequency of each card in the hand. The tree map is particularly useful here because it maintains the keys in sorted order, which is critical for forming consecutive groups. We then iterate through the hand array to populate the tree map with the count of each card. Once the tree map is ready, we proceed to process these sorted cards. Using a while loop, we continue until all cards are grouped or we determine that it's not possible. Inside the loop, we retrieve the smallest card in the map using first key. This card will be the starting point for attempting to form a group of group size. The count variable represents how many of this smallest card are currently available. To form a valid group, we iterate over the next group size consecutive cards, starting from the smallest card. For each card in the sequence, we check if it exists in the map and whether there are enough of that card to match the count of the starting card. If either condition fails, we return false because a complete group cannot be formed. If the conditions are met, we decrease the count of the current card in the tree map by the value of count, as we've used these cards to form the group. If the count for any card drops to 0 after this decrement, we remove that card entirely from the map to keep it clean and efficient. This process continues until all cards are successfully grouped, or we encounter a situation where forming a group is impossible. If we exit the loop without returning false, it means all cards have been grouped into valid sequences of group size. In that case, we return true to indicate success. This implementation effectively combines the sorted order and frequency tracking of the tree map to ensure the solution is both correct and efficient. To begin solving this problem, let's look at the first example where the hand is 1 2 3 6 2 3 4 7 8 and the group size is 3. First, we notice that the length of the hand is 9, which is divisible by the group size, so forming groups is theoretically possible. Next, we create a frequency counter to track how many times each card appears. The counter gives us 1 1 2 2 3 2 4 1 6 1 7 1 8 1. Then, we sort the cards, resulting in 1 2 3 4 6 7 8. Starting with the smallest card, 1, we see that its frequency is 1. To form the group 1 2 3, we reduce the counts of 1, 2, and 3 by 1 each. The updated counter becomes 1 o'clock, 2 1 3 1 4 1 6 1 7 1 8 1. This process ensures that the group 1 2 3 is valid and successfully formed. Now we continue processing the cards in sorted order. The next card is 2, which has a frequency of 1. To form a group starting with 2, we need the cards 2 3 4. Subtracting 1 from the counts of these cards gives us an updated counter, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 6, 1, 7, 1, 8, 1. This group is successfully formed. Moving on, the next card is 6, which also has a frequency of 1. To form the group 6, 7, 8, we reduce their counts by 1 each, resulting in 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 6 o'clock, 7 o'clock, 8 o'clock. At this point, all cards have been used up, and we proceed to verify the final state. In the second example, the hand is 1 2 3 4 5, with a group size of 4. The length of the hand is 5, which is not divisible by the group size. Since it's impossible to form groups of equal size, the output is false. Moving on to the third example, the hand is 1 2 3 4 5 6, with a group size of 2. Here, the length of the hand is 6, which is divisible by the group size. We start by creating a frequency counter, 1 1 2 1 3 1 4 1 5 1 6 1. Sorting the cards gives 1 2 3 4 5 6. We then begin forming groups starting with the smallest card. Starting with the card 1, which has a frequency of 1, we form the group 1 2. Subtracting 1 from the counts of 1 and 2 leaves us with the counter 1 o'clock, 2 o'clock, 3 1 4 1 5 1 6 1. The next card is 3, and again, its frequency is 1. We form the group 3 4, reducing their counts to get 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 1 6 1. Finally, the card 5 has a frequency of 1, so we form the group 5 6. After subtracting their counts, the counter becomes 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock. At this point, all groups have been successfully formed, and the frequency counter is empty 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock. Since no cards are left ungrouped, it confirms that the hand can be rearranged into groups of size 2. Therefore, the output for this example is true. To analyze the time complexity of this solution, we start by examining the key operations. First, the input array hand is sorted using Python's built-in sorted function, which operates with a time complexity of O n asterisk log n, where n is the size of the input array. After sorting, we count the frequency of each card using the counter class from the collections module. This step requires only n time, as it involves a single iteration over the hand array. Next, we iterate over the unique cards in sorted order. Let U represent the number of unique cards. Since the sorting step already ensures the unique cards are in order, iterating over them is proportional to U. Lastly, for each unique card, we decrement the counts 4 group-size consecutive cards in a nested loop. In the worst-case scenario, this could involve processing all n elements in the array, such as when every card belongs to a group. These steps together provide the foundation of our time complexity analysis. Now, let's consider the total cost of decrementing card counts across all iterations. Each card in the hand array is decremented exactly once throughout the algorithm, so the total number of decrements is bounded by n. When we combine all the steps, the sorting operation, which takes n*log n, becomes the dominant factor in the overall time complexity. The remaining operations, including counting frequencies and decrementing counts, are linear, contributing n. Therefore, the overall time complexity of the solution is n*log n. For space complexity, we begin by analyzing the storage used by the counter. In the worst case, where all cards in the hand are unique, the counter will store n keys, requiring n space. The sorted function also creates an auxiliary list of unique cards, which takes u space. Since u is at most n, this space requirement is n. Finally, the algorithm uses a constant amount of space for variables such as card, count, and I, which does not depend on the size of the input. Thus, the overall space complexity is determined by the counter, resulting in n. Now, let's break down the best, average, and worst-case scenarios. In the best case, the cards in the hand array are already grouped into consecutive subsequences of group size. Even in this case, the algorithm must perform the sorting and linear processing steps, so the time complexity remains n*log n. For the average case, where the input is randomly distributed, the same sorting operation still dominates, leading to the same overall complexity of n*log n. In the worst case, where no valid grouping is possible, such as when the cards cannot form group-size consecutive sequences, the algorithm still executes the sorting and linear processing steps, which again results in n*log n. Therefore, regardless of the input distribution, the time complexity consistently depends on the sorting step. To better understand the efficiency of the current solution, let's compare it with a brute force approach. A naive method might involve generating all possible combinations of group size cards from the hand array to check for valid groups. This would require exploring combinations or permutations of group size, leading to a time complexity of n-group size in the worst case. Such an approach becomes computationally infeasible for large inputs. In contrast, the optimized solution we analyzed leverages sorting and frequency counting to handle the problem efficiently. By reducing the time complexity to n*log n and the space complexity to n, the current approach is significantly more practical. Mathematically, the dominant operation is sorting, which contributes n*log n, while the linear steps, such as counting frequencies and decrementing counts, add n. Since logarithmic growth dominates linear growth, the overall time complexity is n*log n. When solving the hand of straights problem, there are a few common mistakes that can trip you up. One big issue is ignoring edge cases, like when the group size is larger than the total number of cards or isn't a divisor of the total cards. If you overlook these scenarios, you might incorrectly assume groups can always be formed when they can't. The solution? Always validate input constraints and explicitly handle edge cases in your code. Another mistake is sorting the entire array unnecessarily, which can be inefficient. Sorting has a time complexity of n-log n, and if you're only working with the smallest unique key, this step is redundant. Instead, opt for data structures like a tree map in Java or collections counter in Python to track frequencies efficiently. Lastly, be careful not to modify the frequency map or any data structure while iterating over it. This can lead to unpredictable results. To avoid this, work with a copy of the data or delay any modifications until after the iteration is complete. Now, another common pitfall is overlooking the consecutive group constraints. It's not enough to assume you can form groups, you need to verify that the count for each card in a sequence is sufficient. For example, if you're forming a group of size 3, you must decrement the count for each card and ensure no count drops below 0. Missing this validation can lead to incorrect solutions. Another inefficient approach is brute forcing every possible grouping permutation. While this might work for small inputs, it quickly becomes impractical due to its exponential time complexity. Instead, a greedy approach is the way to go. Starting with the smallest card and forming groups sequentially ensures efficiency and correctness. Now, in interviews, there are a few key concepts to highlight. First, consecutive group problems often rely on sorting or frequency maps, so focus on reducing time complexity by selecting the right data structure. Second, demonstrating your understanding of greedy algorithms is crucial. Explain why this approach works, such as how processing from the smallest number avoids gaps in the sequence. Finally, edge case handling is just as important as the implementation itself. Be ready to discuss situations where forming groups is impossible and how your code addresses them. Next, let's connect this problem to other related questions you might encounter. For example, LeetCode 406, queue reconstruction by height, also relies on a greedy approach combined with sorting. Then there's LeetCode 659, split array into consecutive subsequences, which shares a similar goal of forming consecutive groups but introduces different constraints to work with. Another related problem is LeetCode 378, kth smallest element in a sorted matrix, which focuses on efficient sorting and heap operations, skills that can be applied when optimizing solutions. Lastly, LeetCode 692, top k frequent words, emphasizes the use of frequency maps and sorting for optimization. Practicing these problems will deepen your understanding of patterns like greedy algorithms, frequency tracking, and efficient data structure usage, all of which are crucial for solving hand of straights and similar challenges. Finally, let's look at some alternative approaches to solving this problem. The brute force approach involves generating all possible group combinations and checking their validity. While this might seem thorough, it comes with a massive trade-off. Its exponential time complexity, O(n), makes it impractical for larger inputs. A more balanced solution is the sorting plus greedy approach. Here, you sort the array and use a frequency map to form groups sequentially. This method is straightforward to implement and balances simplicity with a reasonable O(n) log n) complexity. However, if you want to push for an optimized solution, you can use a frequency map paired with a priority queue or a tree map in Java. This allows you to efficiently find the smallest key while forming groups greedily. While this approach avoids unnecessary sorting and can improve performance, it does come with added implementation complexity, especially in languages without built-in ordered map structures. Understanding these trade-offs will help you choose the most appropriate approach based on the problem's constraints and input size. Great job making it to the end. To summarize, we solved this problem using a greedy approach with a hash map for tracking card frequencies. This method has both practical applications and helps build essential skills for tackling similar problems. If you enjoyed this walkthrough, don't forget to like and subscribe for more tutorials. Keep practicing, and see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!